SwayamPrabha. Digital India. Educated India.
So hello everyone. Today we are going to discuss two-phase passive thermal management technologies, and in this lecture we will be essentially talking about introduction to two-phase passive thermal management. We will focus on conventional heat pipes as an example of two-phase passive thermal management. Just to remind you that passive thermal management can also be achieved, for example, by natural convection, which we have already studied. Here we are talking about two-phase systems, and we will be concentrating on conventional heat pipes. And in this particular lecture, we will see what is a heat pipe and then some industrial applications of these conventional heat pipes. So moving on, let me start with a general introduction to the system. So in many engineering systems, as you know, we encounter transport of momentum, transport of energy, transport of mass. And the universal law which generally dictates this transport, this is what is written here, that the net change which we want, net change in the momentum transfer, or net change in energy, or net change in mass, it depends on the driving potential. That means it depends on the potential which is there to change. And of course, in a natural system, there will always be resistance to change. For example, in this cartoon on the right, we want to convert the chemical energy of the fuel to thermal energy, and then the thermal energy to the kinetic energy of the steam. And then from there, we are running a turbine, converting into mechanical energy. So what are the potentials which are available in terms of chemical potential, in terms of the pressure energy? That will depend on how much net change of energy we are able to do. And then of course, in every energy transport in this domain, we will have some resistance. Now the issue is the relative magnitude of one potential with respect to some other potential will decide which change will dominate, because in a normal system there may be several forces which are acting. For example, gravitational force, pressure energy, kinetic energy, magnetic forces, thermal forces. Depending on which potential will be dominant, we will usually take that as the dominant factor, and then the others are neglected usually in a normal framework when we are formulating the problem. So now, if you see, let's say take an example of electrical energy. In electrical energy, the desired change is the electric current. We want to move the electrons from location A to location B, and there is a potential difference which is available in the form of electromotive force, which is the available potential or the voltage. So we write this change, that net change is proportional to the potential to change, and of course in the denominator will come the resistance, and this is what we call as the electrical resistance, which we write as the potential to change divided the potential to change divided by the desired change. So this is R electrical is equal to V upon I. Similarly, in thermal systems, we have the desired change as the heat transfer, and the available potential to change is the temperature difference. So if you see electrical analogy, the potential difference EMF is related to the thermal potential difference, which is the temperature difference in terms of thermal systems. So Q is proportional to delta T, or analogous to the electrical resistance, we can write a thermal resistance as R thermal as delta T divided by Q. So if you compare this, you see the analogy between the two. This is the potential to change, this is the resistance to change, and this is the desired change which we want from the system, and that is the heat transfer. So we will utilize this concept of thermal resistance frequently in our lecture, and therefore you should understand the universal law, which is the net change is proportional to the potential to change divided by the resistance. The resistance will always come in the denominator, and the potential to change, the magnitude of that, will come in the numerator. So all our equations of change, be it electrical flow or thermal energy flow, they are guided by the same principles. Now the question is, why phase change technology? Why two-phase systems? You have been studying single-phase systems so far. Why do you go for a two-phase system? So let us look at this. So if you see, in a normal convective equation which you have already studied, Q dot is equal to HA delta T, or you can write R thermal as delta T upon Q, and then we can write 1 upon HA as the thermal resistance, which you have already studied. Now, in any thermal systems, they are typically guided by the material constraints. Let the electronic components, you need the silicon doesn't operate beyond a particular temperature. Similarly, IC engines, the let's say the material of the piston and the cylinder liner and other things will dominate the highest temperature which you can reach in combustion. The ambient temperature is usually fixed. So in reality what happens is that the delta T for the designer is actually fixed by material constraints and the ambient. If the Q is increasing, let's say the demand of heat dissipation is increasing, and if you talk about miniaturization, then area is decreasing. So essentially delta T is fixed more or less by design constraint, and for miniaturized systems the A is decreasing. So the only way which we can enhance the Q on the left hand side of this equation is by actually increasing the heat transfer coefficient. Now, how do you do that? So if you see, this is a very typical diagram which you all should understand, and which we should remember also to a certain extent, that at least the orders of magnitude. So if you take examples of natural convection which you have already studied, you saw that with air as the medium, the heat transfer coefficient was of the order of 10 to 15 or 20 maximum, watt per meter square Kelvin. If you use some oil or some water, let us say, then the natural convection can increase, but mind you, this is a log scale here. So it can increase of the order of 500 or so, but then that is the limitation. After that, natural convection, that is the flow which is related to the buoyancy or the change in density which happens because of the temperature gradient. That's the passive flow of fluid which convects in a natural system. Because of the delta T, we are limited to about, let us say, 500 of that order, or 600 watts per meter square Kelvin if you change the Prandtl number of the fluid. Air, of course, is limited to very low heat transfer coefficients. So then what you do is, to increase it to 1 order of magnitude or 2 orders of magnitude, you go to forced convection. So that means now you have an active system. Okay, so you start using a pump. Now if you use air, again you are limited, because air is not a very good convective medium also. The Prandtl number is of the order of 1. And if you then change the fluid, then you can go to 1 or 2 orders of magnitude. You can reach up to 10,000, or of that order 5,000 to 10,000 maximum, because after that the Reynolds number becomes very high and your pumping power becomes very large. So you really don't, you are limited to such values here. Then what do? You change the physics, go from single phase to a two-phase system. That means now you start making use of the latent heat. And as you know, latent heat of water, for example, is very high. And whenever phase change enthalpy is transferred, it's a large amount of heat, and the delta T is very small, because you are actually doing the phase change. So essentially, phase change occurs at isothermal conditions. The pressure and temperatures are locked, and therefore, if you remember your pressure enthalpy diagram, you go to vapor from the liquid phase at the constant temperature line. This is the constant temperature line. So therefore, the delta T becomes very small in that case, and so delta T is very small, and the Q dot is large, because you are talking about the latent heat here. Okay, so it's a large amount of heat. So thermal resistance in a two-phase medium becomes very small, or you can say that H is very large. And you can see here in phase change heat transfer, for example, boiling, etc. Heat transfer of the order of 10 to the power 5 watts per meter square Kelvin is easily possible. So therefore, you can have active two-phase systems like flow boiling, or you can have passive two-phase system. We will of course concentrate in this lecture on passive two-phase systems because they are proven to be the best solutions for variety of thermal management issues. They are passive. They have very large heat transfer coefficient. They make use of the latent heat, and there is no external pump which is required to run these systems. So let us take an example of the heat pipe, which is the most convenient and the most interesting, two-phase passive technology. So what is the difference between active and passive? Active cooling of course requires electrical energy like a pump. Passive cooling requires no active source of power. Of course, please remember that refrigeration requires lowering the temperature below the ambient and requires electrical work for achieving low temperature. So we are not talking about a refrigeration system here, okay? We are talking about a heat transfer system. And if you see active systems, then you can have liquid pump looped, you can have a liquid which is there is a pump which pumps the liquid to a electronic chip, and then this liquid comes back here. This is all single phase, okay, and this is like an active system because the pump requires some energy or work has to be done on this pump for liquid to circulate in this circuit. Peltier cooler, if you remember, is an example of active refrigeration. But what we are going to do is we are going to use a passive sink, like a passive device where there is no electrical work, okay. So heat will get transferred from one location to the other. Mind you, we are not talking about refrigeration here. We are only talking about a passive device by which heat can be transferred from location A to location B without any external power source requirement. So now comes the question, what is a heat pipe? How does it achieve this passive thermal management? So if you see the definition of a heat pipe, it says that it's a synergistic engineering structure which is equivalent to a material having a thermal conductivity which is greatly exceeding to that of any known material. So now it is like a superconductor, which means like it's a superconductor. Okay, so how does it work? So let us see the construction of a heat pipe. Now heat pipe in the most simplest form will be a tube, a simple tube. It can be a copper tube or a stainless steel tube cylinder, and it will be let's say evacuated. It will also have a wick, which you can see here, which in the cross section we can see the wick here, and once you evacuate this system, and then when you evacuate, there is nothing inside. It becomes devoid of material, and then you put only enough liquid inside it, some liquid. Let us say right now, for the sake of discussion, we will take copper water heat pipe. So it's a copper tube, let us say, and the working fluid which we will fill inside is water. So as soon as the water goes inside a vacuum medium or a vacuum space, naturally it will flash or it will evaporate, in a sense that it will like cavitation. Thermodynamics will ensure that equilibrium condition comes very quickly because it's the liquid gets stretched because of the low vacuum inside, and then naturally there will be evaporation, mechanical boiling like cavitation, and some liquid. The liquid will go and rest in the porous media, which is the wick structure, which is all around. So it is wrapped around it. So I can make a diagram here. You can see that the porous media in the cross section is looking like this, something like that. So because of the capillary action, the liquid will all go inside and rest, and the vapor will come in the vapor space here in between, which is the annular space. This is the vapor space. Okay, and if you have a pressure transducer, if you have a pressure transducer which is attached here, it will start showing the saturation pressure which is corresponding to the temperature at which this pipe is in the room. So if it is the room temperature and if it is water, it will show the saturation pressure corresponding to the room temperature for water. If it is ethanol, then it will show the saturation pressure corresponding to ethanol at the room temperature, which is, let us say, 25 degrees centigrade. So your phase tables or thermodynamic property tables will tell you what is the saturation pressure corresponding to the temperature at which the heat pipe is stored. So that will be the pressure which will start showing, and of course the temperature will be the local temperature of the room where you have done the filling, and equilibrium will come, and the heat pipe, all the liquid will be in the capillary region. It will be here, and we will put only enough liquid so that it saturates this wick, and not more. So there is no extra liquid. All the liquid goes in the porous media, which is at the periphery, in the circumferential periphery of this cylinder, and the in between space is filled up with vapor. This single component two-phase mixed working fluid is in equilibrium. It comes to equilibrium eventually. Initially when we were filling, it was in non-equilibrium because there was vacuum inside, but eventually if you give enough time, it will come to an equilibrium position. Now the heat pipe is ready to operate. So please remember, there is a single component two-phase system inside the pipe, and now let us see what happens if you heat a particular side. So let us say this side is heated up. Okay, so when you heat, it is called as the evaporation section. Naturally there is no pool boiling here, it is only evaporation at the interface, and you can see because of the porous media the interfaces are formed here. And if you will recall, the Young-Laplace equation and the Clausius-Clapeyron equation has to work together for this system to start working. So of course there will be a Young-Laplace pressure difference because you have an evaporator section here and the pressure is increasing, and therefore the local pressure here in this region will increase, and this pressure of the vapor is higher than the pressure in the liquid. And therefore across the interface there will be a depression of the interface, and the curvature will be dominated or will be determined by the Young-Laplace condition. And then you can imagine the other side is getting condensed, or the other side is subjected to a cold temperature. So you have the heat source on one side, the heat sink on the other side. So the pressure here is lower, of course, because of the cold conditions which are here. They corresponding to the saturation, local saturation pressure, which is lower, and local saturation temperature, which is lower than on the evaporator side. So what will happen is that the vapor will start flowing in a certain direction from the high pressure area to the low pressure area. Mind you, the pressure difference is not very high because we are essentially we are disturbing the equilibrium, and just around the equilibrium, depending on the amount of heat which is coming in, the latent heat is being used, the vapor is being generated, and then it is flowing towards the condenser. At the condenser side, condensation will occur at the interface. The liquid, the vapor pressure and the liquid pressure will be more or less the same, and therefore the meniscus will be flat. That means the radius of curvature is nearly infinite. It's like a flooding condition there. And then since the liquid pressure here is higher than the liquid pressure here, there is a capillary pressure difference, and therefore the liquid will come back passively to the evaporator. So you can see here A to B, there is a phase change process, then B to C, the vapor goes to the condenser, then it condenses, and then again it comes back. So in this way a passive system is generated, which the pumping of this fluid, the vapor towards the condenser and the liquid from the condenser to the evaporator, this is brought about by the capillary pressure delta P, capillary, because of the capillary wick which we have introduced on the circumference inside this heat pipe. So in this way a lot of latent heat is transported from location A to location B, that is the evaporator to the condenser, and since the delta T is not very high because we are working close to the equilibrium conditions, the delta P between this point and this point is not very high, and therefore the delta T is also not very high. because here is the local saturation pressure corresponding to the evaporator and the local saturation pressure corresponding to the condenser, and therefore you see that the thermal resistance is nearly zero. And you can see at a very low thermal resistance, a large quantity of heat gets transported from the evaporator section to the condenser section, and that is why it is defined like a synergistic engineering structure, which is equivalent to a material having a thermal conductivity greatly exceeding to that of any known material. So this is the way a heat pipe works. I hope you have understood it. Now we will see more and more examples in the coming slides. Just to give you a brief background, the historical development of heat pipe before we take up more examples of the modern day industrial usage. A series of patents were filed by the Perkins family, which were like which were structures which were similar to a heat pipe. We'll talk about it a little later. They were called as thermosiphons. They didn't have any weak structure, and they were only operated by gravity. So right now I have not introduced them to you, but you will see that they are simpler than heat pipes, and they were patented long back in the 19th century. Then the capillary structure, the way we have seen just now, was introduced by Gaugler in 1944 in General Motors Corporation, and then this particular device rested in the GM Corporation internal files for many years, and in the Los Alamos National Laboratory, it was sort of reinvented in 1962 by Grover, and then of course later on it was understood that before Grover, GM already had this type of a development internally in 1944. Grover gave the name heat pipes in 1966 patent, and then an analysis was later on simultaneously done by the first paper of a proper analysis in 1965 by Cotter, and then within 2 years, the heat pipes started, flying into the space. Because they were such a interesting, such a powerful, and such high efficient systems. They were passive, so the space agency was very happy because they don't require any active power on space to cool their thermal systems or cool their devices, electronic devices, and then the heat could be taken away from the satellite and it could be radiated to outer space by the radiators which were there on these space vehicles. All the initial efforts in the 60s, the late 60s and the 70s were in the space domain. It was supported by the space industry in US as well as in Russia, for example, and then slowly it percolated into terrestrial applications. And then now of course heat pipes are there in space as well as in terrestrial applications in a big way. And of course newer designs of heat pipes have also come in the market, which we will talk about in the later part. So this is a brief summary. I will not go through each one of them, but you can read it. How since 19th century, and up to the modern day development, these papers are available in the classical literature. And different designs like cryogenic heat pipes, rotating heat pipes for temperature control, and various other types of variable conductance heat pipe, for example, were developed. So without going into the details of this, in the 70s, NASA Ames had the heat pipe space experiments. The heat pipe flew in space. Later on, different other designs of heat pipes like arterial heat pipes, inverted meniscus heat pipes, etc. were developed. And then in the recent past or recent history, micro heat pipes came. After that, the loop heat pipes and the pulsating heat pipes or oscillating heat pipes were introduced in the 1990s. In between, of course, we have development of capillary pumped loops and loop heat pipes, which we will talk about in the later lectures. The literature is available throughout in many different forms. Of course, the International Heat Pipe Conference, it started in Stuttgart in 1973 by Professor Manfred Groll. And then this conference, this popular conference of the heat pipe community has traveled throughout the world, as you can see. It was also held in 2013 in Kanpur. at IIT Kanpur, in fact, and now 2023 it will go to Melbourne in Australia. Several books are available on heat pipe technology, starting from Dr. Chee's book in 1976, Dunn and Ray, Ivanovsky, Peterson, and Professor Fagri, Amir Fagri in 1995. And then, of course, if you see the literature, various international journals on heat and mass transfer and thermal science are replete with papers on passive two-phase thermal technologies like thermosiphons, gravity thermosiphons, conventional wicked heat pipes, loop heat pipes, capillary pumped loops, pulsating heat pipes, micro heat pipes, and other types of heat pipes. So why are they used? Because you can have a wide temperature range of operations depending on which fluid you take. It has a high transport capability at very low driving temperatures as we have seen. You can have, I mean, we have just seen the example of a simple cylinder, but you can actually have various geometric shapes which have wicks inside, and therefore they are very convenient for engineering design applications. The heat source and the sinks can be isolated with each other, and you don't lose any thermal potential. The temperature at the evaporator is more or less the temperature at the condenser, and therefore you have not, without any voltage drop. In fact, we are able to transport a lot of current or heat in this case. So it is like a superconductor. Electrical superconductor can be made analogous to a thermal superconductor. So heat pipe is like a superconductor. Then it can function as a transformer because you can go from a small area high flux to large area low flux at the condenser, and you can also give isothermal conditions because the entire heat pipe is more or less at the same temperature. So wherever you require isothermal sources, like in radiation pyrometers, for example, or in an application of a uniformly heated oven, you can use heat pipes. And of course, needless to say, they are highly efficient passive heat transfer elements with no noise. They are maintenance free. That's why space industry loves them. And they are simple to design. There are no moving parts. And these are some of the examples. These are some of the attributes of why heat pipes are used. What are the working fluids? Now it depends on what temperature you want to transport the heat. So as you can appreciate, heat transfer is always done at a certain delta T depending on the engineering application. So if you have high temperature requirement, so let us say a radiation pyrometer, or for a standard isothermal high temperature radiation source, you can use silver or lead or sodium, for example, or cesium, potassium, at very high temperatures. In the medium temperature range, we can use sulfur or mercury or dotherm. For example, at low temperature, one can use Flutec. These are specialized organic or non-polar fluids which are developed for electronics cooling application. Then one can use ammonia or water, ethane, for example. And then for cryogenic applications at very low temperatures, you can use oxygen, nitrogen as the working fluid. So mind you, these are the working fluids. Okay, this is the working fluid of the heat pipe which you are filling inside the heat pipe. And then depending on its thermophysical properties, its freezing point and the melting point and the critical point, you can then, depending on the application, one can choose the right fluid for the right application for the right temperature range in which you would like to transport the heat or operate the heat pipe. Now, as you know, this particular fluid is inside the wick. So you have the container, you have the wick around it, and then the fluid is all saturated inside the porous wick. And we want active life of a heat pipe to be, let's say, 10 to 12 years. In a space application, for example, a satellite may require a life of 7 years or 12 years. Space vehicles may require longer periods of time. And even for terrestrial applications, for example, solar heating or other type of application, electronics cooling, laptop cooling, The typical life may be of 5 to 7 years. And during this time, the idea is that this fluid should not react with the porous material and form some gases which are harmful for the heat transfer to take place. So therefore, if you are using water, then one can use stainless steel or copper, nickel, titanium. But if you use aluminum water, then the aluminum will react, it will oxidize, and it will form aluminum oxides, and hydrogen gas will be generated inside this heat pipe. And this hydrogen gas, as you know, will hamper the heat transfer, because it will go and collect in the condenser area, which is the coldest part of the whole device, and it will block the condenser. And the heat transfer, as you know, condensation heat transfer is very severely affected by the presence of non-condensable gases, and therefore aluminum water heat pipes are not possible. Similarly, ammonia, copper is not possible. They will react, ammonia and copper will react. Again, hydrogen gas may be generated, inside the system. Similarly, methanol, acetone, lithium, sodium, they are compatible with certain materials and they are non-compatible with certain materials. So one has to be careful about while choosing the combination of the liquid and the working fluid and the container. So the container also comes in contact with the fluid, and therefore it is equally important that the working fluid does not react with the container also during its entire lifetime. Now we will move on to section 2, which is the application of heat pipes. So we will first see the applications of conventional heat pipes, and then in the next lecture we will see how exactly to model it, and we will try to understand the pressure differentials which are created inside the heat pipe, etc. So the working will be done in the next lecture. We will first see the applications. So, because of these very attractive properties of the passive two-phase technology with such a large heat transfer coefficient, the heat pipes are used across the several industries, from aerospace to electronic thermal management, heat pipe heat exchangers, ovens and furnaces for isothermal conditions, medical applications, transportation and de-icing systems, manufacturing industry, solar systems, and of course space. So space is the starting point of the journey of the heat pipe development. So you can see the International Space Station here, and this has these radiators which are there, deployable radiators, and a lot of heat is generated in many of these subsystems. This heat is brought to the radiators, and then inside the radiators you can see these cylindrical heat pipes to isothermalize and spread the heat on these panels of the radiator. Here is another example where a vapor chamber like a heat pipe is embedded, and then on the heat pipe there are these fins, and then of course air is blown or natural circulation is there, depending on what type of technology is applicable in a particular electronic package. So here again in the electronic systems, here you see 3 heat pipes, 4 heat pipes in fact, which are connected to a heat sink here with fins, and then the electronic component, the power electronic component can come here, and then you can see that now the 3-dimensional structures are possible. The heat pipe is bent in a 3-dimensional fashion. There are 4 heat pipes in fact, and they will transport heat from this heater towards the heat sink. Here you see a typical laptop cooler, and all of you have laptops, and you can see that behind the laptop you can see you can feel hot air coming out, and this is through this fan, and air is blown over here, and the microprocessor chip is here, and this is the heat pipe. This is a 3-dimensional bent heat pipe, which is connected here between the heat source and the heat sink, and the heat is transported from the microprocessor through this heat pipe to the fins, and from this convective heat transport to the air which is blown by the small fan. Here again you see an IGBT cooler, 3 heat pipes, 2 of them are bent and 1 of them is straight. And again you can see this is like a very small area where the heat is collected from IGBTs, and then it goes to the large area here. So naturally there is air flowing over here, so the edge outside and the area here is much more than the edge here is high, and so the edge of the heat pipe and the A1 is small, and here the H2 is small and A2 is large. So in this way heat is getting transported from location A to location B and very efficiently. So if you see any electronic package, it has multiple functions. You have it has to support the architecture. It has to transfer proper signals. The conditioned power has to be given to from the transformers to the electronic devices. And of course a very important function is to dissipate the heat generated to maintain safe working temperatures, and then to give mechanical support and environmental protection. So this heat dissipation in many of the modern electronic systems is actually done by heat pipes. And if you see here any chip or a die, the silicon chip is here. It is mounted on a substrate carrier, and then there is a casing, and finally is the ambient. So there are various levels at which cooling is required. So from chip level to the substrate level, it is usually conduction heat transfer, and then to the casing it can be via a heat pipe. So for example, heat pipes can be embedded like this, or it can be put like this. So there are various let's say configurations of heat pipes and on which electronics can be directly mounted. For example, as you can see here, flat plate heat pipe with the mounting of electronics chips directly on the heat pipe. So there are various ways at which this is level 2 and level 3 cooling from the substrate to the casing, and from the casing to the ambient. This can be brought by a smart combination of heat pipes and heat sinks, and making use of either natural convection or forced air cooling at the end. But the internal transport is from a passive system, which is the heat pipe, so as to get the advantage of the superconducting behavior of this particular device. So here again another example where electronics cooling or IGBT cooling. You can see several heat pipes. They are connected to a thyristor. Here you again see a power transistor which is connected to a heat pipe and a heat sink. Here again the heat pipe, whose cross section can be seen here, with slightly elliptic type of a heat pipe, pressed heat pipe for notebook cooling, for laptop cooling, for example. So the microprocessor is attached here, or this particular block is attached to the microprocessor, and the heat which is generated from the microprocessor of the order of 20 to 40 watts is brought to the heat sink, where the area is very large. The temperature here and the temperature here are more or less the same, because of the heat pipe, and then you blow air over it to get it cooled. So in this way thermal power from the microprocessor is dissipated to the ambient. Here you see more examples of electronics cooling, and as you can see, depending on the technology, you can have a thermal resistance of 3 Kelvin or 3 centigrade Celsius per watt to nearly 1 order of magnitude low, 0.3 centigrade per watt. It essentially means that if you have a 20 watt or a 30 watt device, you multiply it by 0.3, so that is like 6 degree delta T, or 9 degree delta T will be there between the hot end and the ambient. So you can see various packages which contain heat pipe or vapor chambers, or different designs, 3-dimensional designs, bent designs, flat plate designs, which are part of the electronics cooling industry. Various examples, so one can have sintered powder wick, or we can have actually grooved heat wick. We will talk about it in the next lecture when we see the details of the construction of the heat pipe and its working operations and the physics of heat transfer. Here we are more interested in seeing the application. We can also do from a two-dimensional electronic package, one can also move on to a 3D package. So here you see some examples of small 3D packages of the order of 8 to 10 watts, from Alcatel or Nokia, or other companies which manufacture or which are experts in such type of 3D manufacturing, where heat pipes are also embedded as part of the thermal management strategy. So here you can see another example of a 3-layer modular horizontal package which has flat heat pipes. So these are the heat pipes in fact, and 3 of them you can see, 1, 2, 3, where the electronic chips are directly mounted the way you can see it here on the heat pipe, and then the heat pipe works as a spreader plate. You can see the spreader plate here, and it isothermalizes the hot spots of the system. So here you see such a modular heat pipe in the final design, and this is at the stage where the heat pipe is getting filled with a valve. Later on, this valve is removed from here, and you can do a pinching and a welding here, so that there is no air leakage from outside to the inside or inside to the outside. It becomes an isolated system which has only the working fluid inside and its vapor. It is very important that any non-condensable gases are not formed inside by chemical action, or air is not mixing with the two-phase system which is inside. Otherwise, the performance of the heat pipe will go down drastically, the thermal resistance will increase, and which is not desirable. Then you can have, for high temperature applications, liquid metal heat pipes, as I said, like sodium or potassium. And you can see for isothermal furnace liners, or for making black bodies which require isothermal conditions, the typical range can be from -50 to 300, wherein ammonia or water can be used, and then beyond that, up to 1000 degrees, liquid metals can be used. Similarly, solar receivers, depending on whether they are concentrator type, they can operate at very high temperatures, and one can use as the heater heads of Stirling engines or generators for power generation in solar dish systems. So this is like the high temperature range of applications of typical heat pipes, where sodium and stainless steel or Inconel are used as the wick material and the wall, and the operating temperature will be from 600 to 1100 degrees centigrade. They can really operate very efficiently, and they are actually in operation. There are several problems which are there when we apply high temperatures, because there is corrosion at high temperatures which is very high. Impurities can lead to a lot of damage, and therefore cleaning, degassing, annealing, these are some of the things which must be done. Hydrogen diffusion is also a problem, and therefore like enamels or coatings are used so that at these high temperatures these diffusional problems are avoided, or oxidation problems or chemical corrosion is avoided. Then one can also make large heat exchangers, which are for let's say thermal energy recovery. So hot air can flow in half of the heat pipe, and this heat pipes can then transport this heat from the hot let us say exhaust gases to the incoming gases for boiler operation or for some other industrial use. One can also make evaporation condensation loops like this, wherein the hot air is used to boil a certain fluid, the vapor travel upwards and then they are condensed. Here you can heat up certain gas or air, and then this liquid falls down, which these are called as separate type of heat pipes. They may or may not use any wick, but with a gravity action, since the gravity is working in this direction, the vapor goes up, and the liquid comes down, and these are like thermosiphons, so large heat exchangers, heat pipe heat exchangers can also be made by thermosiphon action, the way it has been shown here, or it can be also used by wicked heat pipes, cylindrical heat pipes. Many of them make an array, and this array is then properly arranged, so that half of it is in the inlet side and half of it becomes the evaporator, and the other half becomes the condenser, and heat transfer can take place from the evaporator to the condenser. This is one example where an heat pipe heat exchanger has been used at this location here, and you can see hot air coming in and then the cold air becoming hot. The heat recovery systems for district heating has been employed in an industrial application. These are for power plants. Again, one can make large heat exchangers with heat pipes, wherein the flue gases the enthalpy is taken out from the flue gas, and it is given to secondary air, which is used for the combustion application. One can also use heat pipe for geothermal energy harvesting, where heat pipes can be used effectively at various places to take out heat from within the earth, and bringing that heat in the vapor form to run an electrical generator, for example. So there are various applications depending on the operating temperature, the power requirement, the heat flux which is available, and the geometrical construction constraints which are there in real-time applications. So you can see the collage of industrial applications, cooling of electronics, energy systems where heat pipes are used, environmental devices, permafrost stabilization, for example, then vapor chambers for electronics cooling, heat sinks embedded with the heat pipes, coupled with natural circulation or natural convective heat transfer, very high heat flux modules, bent heat pipes in the form of U or other L shapes or T shapes, for example. In the aviation sector also, a lot of heat pipes are being used now for thermal management of electronic equipment, and also the entertainment seat electronics equipment. So we will see some more examples as we go along. Also, heat pipes are used in automotive applications for heat recovery, for LED lighting, thermal management of LED lighting, and things like that. So finally, to close the lecture, let us look at the advantages of heat pipe heat exchangers. They are very high level of redundancy is there, little maintenance, compact designs. You can have isothermal elements. You can separate the gas portion. There is no cross mixing, for example. They are of course passive with no moving parts, and therefore they are cost effective, and heat pipes can be easily assembled in heat exchanger format, the cylindrical vessels, as you have seen in the examples. So to summarize, in this lecture, we have appreciated the difference between active and passive thermal management systems. We have been introduced to passive operation of a heat pipe involving liquid vapor phase change technology. So as you will recall, the liquid gets converted to vapor by taking the latent heat from the evaporator section. The vapor pressure increases locally. The vapor travels to the condenser side, where because of the low temperature existing outside, it condenses, and now the liquid has to be brought back to the evaporator by the capillary action. So we have also seen several applications of heat pipes in various industries, in space, in avionics, in furnaces, in high temperature applications, in heat pipe heat exchangers for power industry, thermal power plants, and of course commercial electronics like laptops and power electronics devices. So with this, we come to the close of lecture. If you have any questions, of course, you are welcome to contact me. Thank you very much.